Hello again, and we're going to continue our conversation dealing with chemical bonding. And today's lesson will be specifically on covalent bonding. This is part one. It'll take us a number of days to deal with covalent bonding and all the different topics that we're going to address. If you remember, covalent bonding deals specifically with, as we look at our periodic table, with just the right side of the periodic table, or the right of the stair step, the nonmetals, kind of with the exclusion of the noble gases, because the noble gases typically don't bond because they already have a full valence shell. And so we're not really worried with them. So we're actually looking at a very small selective group of elements. And what we're looking at is a couple of the trends that we talked about from last chapter, like ionization energy and electron affinity. Ionization energy was trying to push out an electron, and if you remember that ones like nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, those guys, they have a high ionization energy. In other words, it's hard for them to lose an electron. Very difficult. They don't want to lose electrons. On the other hand, they want to gain electrons. They have a high electron affinity. They want to gain electrons. So because of that, you run into a problem. Whenever you have a nonmetal bond with another nonmetal, so nitrogen bond with oxygen, or sulfur bond with chlorine, or something like that, where you have nonmetals bonding with other nonmetals, the problem that you run into is they all want to gain, but none of them wants to lose. So you have sulfur, it needs to, and it wants to, let's say, pull those from chlorine, but chlorine doesn't want to give its electrons up. Chlorine wants to pull them from sulfur, and so how do you end up solving this problem? Well, we end up solving this problem, if we look at really what the definition of covalent bonding is by sharing electrons, and that's what covalent bonding is. They're bonds consisting of shared electrons. So we kind of solve this whole problem of dealing with nonmetals wanting to pull electrons away from other things. When nonmetals want to bond with themselves, they end up sharing electrons. Now, this is not a nice, peaceful sharing. They're both it's kind of a game of tug of war, and they're both trying to pull those electrons away from each other, and that will result in something a little bit later that we'll talk about called polar bonds, but we're not going to get into that right now. So you have the nonmetals don't give off electrons, so as a result they're forced to share electrons in order to complete their octet. Now, completing the octet is a key thing here, because as we dive into this, everything we're doing is to complete that octet, to get to 8 valence electrons. So if I start with 7, I know I'm going to need one more to complete that octet. If I start with 6, I know I'm going to need a couple more electrons, but I'm not transferring electrons like in an ionic bond. Instead, in this case, I'm sharing. So I'm going to have to share. If I have 7, I'm going to have to share one more electron with somebody. If I need 2, I'm going to have to share 2 more electrons in some way to complete that octet. So that's more or less what we're going to look at. And the way we're going to do this is we're going to look at what we call electron dot structure, or the Lewis dot structure, to show how these atoms partner together and how they come together as we do this. So we're going to take a look at that here. All right, here we go. Here's what we mean by using electron dot structure, or what's sometimes referred to as Lewis dot structure, to illustrate what we've got going on here. So you've got your electrons here demonstrated around your chlorine atoms. We're going to choose chlorine. It's a nonmetal. It's got 7 valence electrons. So we're going to start with what's called a single covalent bond. And in a single covalent bond, you have a situation where, there we go, let's get that out of the way of the glare so we make sure we see all of the dots. In a single covalent bond, what you've got is one shared pair. That's kind of more or less the definition, is one shared pair. And right now, our current chlorine atom, it has 7, it needs 1. And because you've got a covalent bond, it's going to share that. So we're going to draw another chlorine atom, and the way we draw this is we draw them right next to each other. So here's our other chlorine atom, and we'll draw on our valence electrons here. And I'm actually going to use a different color, and you can use a different color if you want to use a different shape instead of dots, if you want to use an X or whatever. I'm not going to be real picky. We're going to use a different color to show this other electron that belongs to this chlorine atom here, and showing that this is the shared pair. So what happens is this. In a sense, they both borrow an electron from each other. This electron originally belonged to this atom, but this atom is now borrowing it. This electron originally belonged to this atom, but this atom is now borrowing it. And they're both kind of tugging on these electrons. They're sharing them. And so as a result, these two electrons belong to both atoms. And so as I count my electrons now, I have these two belong to this atom, as well as these two. That makes 4, 6, 8. So now I have an octet. I have 8 valence electrons. My atom has lost energy. It's stable. Same thing applies to this atom. You have your 2 in here in the middle, what we call your shared pair. And then you have 2 here, 2 here, 2 here, for a total of 8 valence electron. So on both atoms now have 8 valence electrons. They've completed their octet, they're full, and they are satisfied and stable. And that's how we draw what's called a single covalent bond. You can also draw this using what's called a structural formula, and I'm not going to spend a lot of time with this, but to represent the bond, what you can do instead of drawing the dots there, or the shared pair, is we can represent that using a dash, okay, or a line in between them. And if you have one line that will represent 2 electrons, or the shared pair that's between these two, and it shows this bond. It's representing the bond between them. One line would represent a single covalent bond. Now, what if an electron or an atom had fewer than 7 electrons? This one, chlorine, was easy because it had 7 and only needed 1. That was easy peasy lemon squeezy stuff. But what if you have, let's say, something like oxygen? And oxygen has 6 valence electrons. So it has 2 paired electrons and then 2 electrons that are unpaired. It will always be the unpaired electrons that are involved in bonding in a covalent bond. And so I need one of 2 things to happen. Either I need 2 single bonds here to complete my octet. So a single bond here would give me 1 more electron here, and a single bond here would give me 1 more electron here. But let's say I don't have something to bond to this, and so I can't form 2 single bonds. What I can do is form a double bond. I can only form a double bond when I have space for 2 here, or more. In this case, I have space for 2 electrons. And so let's say I'm going to bond another oxygen. Let's say I have another oxygen over here, and this other oxygen also has 6 valence electrons as well. And we'll draw these last 2 electrons as blue electrons because they're going to be the ones that are involved in the bonding process. So I would normally draw oxygen like this. Now here we have these 2 in the middle. This would be what we would normally refer to as a single bond, but obviously that doesn't work because I'm still missing an electron from each one. So how do I solve this problem? Well, what if I do this? I shift these electrons all right here in the middle. So I place them together, and what I end up with is 2 shared pairs. So here's one shared pair, and here's the other shared pair right here. So 2 shared pairs for a total of 4 electrons in the middle that are being shared by both, or that belong to both, if you want to look at it that way. And so I count, here's 4, plus 2 here, plus 2 here. That's 8 around this atom. 4 here, plus 2 here, plus 2 here. That's 8 around that atom, and I'm good. I have 8 around both, and I've completed my octet. And again, if I want to represent this a different way, I can use what's called structural formula. And then let's go ahead and erase this. In a structural formula, I would show 2 dashes to show that there's a double bond here between this. And then I would fill in my other valence electrons that are around the edge here. And the ones that are unbonded, these other electrons, one thing to note, whether it's a single, double, or eventually a triple bond here that we'll talk about, these around the edges or the perimeter always come in pairs. You'll never find electrons here that are by themselves. Okay, these ones here were the unpaired electrons, and now they're paired and as they share their electrons. So this would be what we call a double covalent bond. So far, hopefully pretty simple. And you can imagine the last thing we're going to discuss today, if we have a single covalent bond and we have a double covalent bond, there is also a triple covalent bond. And no, I know you're thinking, what about a quadruple covalent bond? No, there is no such thing. So let's say we have nitrogen here. We have a nitrogen atom here and a nitrogen atom here. And nitrogen is normally written, you have its valence electrons like this. And over here, the other one has the same situation. Each one has 5 valence electrons, and so each one needs 3. And since each one needs 3, how convenient. Okay, they've got 3 unpaired electrons to share with each other. Remember, it's the paired electrons here on the outside. Those are not involved in bonding. It's only the unpaired electrons, the ones that don't have 2 on whatever side they're on, or whatever orbital. Remember, these represent orbitals. And so what I can do to satisfy this bond, if a single bond won't work or a double bond won't work, then you can use a triple bond. And so in this case, I'm going to move all my unpaired electrons to the middle. And we're going to end up with 3 shared pairs. And so you have 1 shared pair here. I'll go ahead and circle that. These guys right here is 1 shared pair. My second shared pair is right there. And my third shared pair is this guy right here. So I have 3 shared pairs in the middle for what we call a triple covalent bond. And again, if I wanted to count, and you probably always do to make sure that you've actually reached 8 valence electrons, I can count here 3 shared pairs. That would be a total of 6 electrons here in the middle that belong to both of them. And then I've got 2 on the outside, so 6 here plus 2 on the outside gives me 8. So this guy has 8. And then 2 here plus the 6 in the middle. This guy has 8 as well. They both have 8. Their octets are complete. They've lost energy. We're good to go. We now have stable atoms. And so we would write this as N2. It is complete. And again, we can do the same thing with the structural formula if we wanted. Instead of writing the dot structure here, what we could do instead, if we wanted to, is we could write that line. And in this case, it would be 3 dashes or 3 lines representing that there is a triple bond going on here. So that's a little bit about single, double, and triple bonds. Again, single bonds involve a single shared pair. Double bonds involve 2 shared pairs. And triple bonds involve 3 shared pairs. And later on, we'll do some practice in class working with electron dot structure and structural formulas, how to draw those, what happens if you don't have nitrogen bonding with itself, what if nitrogen was bonding with, let's say, oxygen and chlorine. How would you do that? How would you figure out and draw the pairing for those? How would they combine? And so we'll do that in class.